welcome to part 2 on the topic measurement quantities and units. This is actually the last section of this topic, and it's going to be about dimensionally correct. If I want to just do a recap on everything we did so far from the last video, in case you didn't watch it, we talked about fundamental quantities, derived quantities, and how to turn an equation or a quantity into its dimensional formula or its derived formula, but basically changing the derived formula into a fundamental formula. A fundamental quantity is a quantity which is independent of other measurement quantities and is not like described in the form of any other quantity apart from itself. And we have derived quantities which is gotten from the combination of one or more fundamental quantities. Then we have the supplemental quantities, which are derived quantities without units that are held joined with fundamental quantities. There are quantities without units that are joined with fundamental quantities to form other derived quantities. We have stuff like phase angle there, but we're not really going to use that. So I'm going to move head but into dimensionally correct. If you come across this term dimensionally correct, when they ask you if something is dimensionally correct, they're basically saying, is everything in this equation correct? Is, like, let's do, for example, we're going to do A plus B is equals to C. And they tell you that, is this equation A plus B equals to C, is it dimensionally correct? They're basically asking you if this guy here is the same thing as B and also the same thing as C. So A, B, and C, their dimensional formula have to be the same. So that's just the basis of dimensionally correct. If they're asking if something is dimensionally correct, we're asking if they all have the same dimensions. So I'm going to move straight and I'm going to be able to explain it better for you to understand better if through I use a question. So I have a question right here, and this question has 3 in it, so we can easily understand it. So it says, which of the following equations are dimensionally correct? Which of the following equations are dimensionally correct? We have the first one is S equals AT plus BT squared. The second one is AT is equals V plus U all over 2. Then we have S is equals UT plus AT squared. So they're basically asking, is S equals to an AT and VT squared, are they the same thing dimensionally? Is AT dimensionally the same thing as V plus U over 2? Is S the same thing as UT plus AT squared dimensionally? So I'm going to move straight into it. Now I have the fundamental quantities here in case you might not have watched the previous video or you can't remember most of them. You can use it as far as a reference: mass, length, time, temperature, current, amount of substance. So we're going to move on. Our first question is S is equals AT plus VT squared. Yeah, our first question of S equals AT plus VT squared. I'm just going to write that down. We're going to solve it now. S equals AT plus VT squared. Okay, so dimensionally correct. We're going to see use the same pattern of solving for dimensions to get it. We're going to get dimension for S, then dimension for AT, dimension for VT squared. So let's look at the S. If you're familiar with physics, S denotes distance. So through distance is the length that is moved by an object. That's the definition of distance according to physics. And so that means distance is the same thing as length, which means it's already a dimensional unit, a fundamental unit. So I'm just going to write it down as S is already L. So we've gotten our first dimensional. I'm going to be solving on a different page, but putting the answers down here. Then let's look at AT. AT. A, acceleration. Acceleration is the velocity. Is change in velocity with time. Acceleration is change in velocity with time, which means that it is a derived unit. It's gotten from velocity and time. Acceleration is change in velocity with time. Now we have time is already a fundamental unit, thank goodness. But velocity now is the issue. Velocity is another derived unit. So we have to break down velocity again into its dimensional formula. So velocity is the distance or is displacement traveled with time. Velocity is displacement traveled with time. Displacement is the same thing as distance. We're going to write V is equals to D, which denotes either distance or displacement with time. So we have successfully broken velocity down to its dimensional formula. Into a simple formula. If we want to change this dimensional formula, we know that distance is the same thing as length, so we're going to write L, and time is tt, so that's capital letter T. So we know that velocity is distance over time, which is L over T. So that means our A is equals to, this V over T, let me just go back to it, is the same thing as saying V times 1 over T. V times 1 over T. Sorry, this is a bit hard to write on with my hands. V is equals 1 over T. Okay, that's better. So, which means you're going to put it as V. V is now L over T dimensionally. That is L all over T times. T is also a fundamental unit. So that is 1 over T. So L times 1 equals L, and T times T is T squared, which means that acceleration is LT squared. But remember, if you watch the previous video, I'm sorry, I didn't take a picture of the rules. The rules for dimension, turning something into dimension, rule number 1, you have to write them down to their formula. Write them down according to their formula. The second rule is remove any constants, things like numbers, pi, all those things are not actually members of the formula. They're just exact numbers according to chemistry, or they are just distinct or definite numbers. Things like that are not mathematically a formula quantity, we remove them. And the third rule, so which actually what I'm going to use, goes with the law of indices. Number, I think is the last rule, I'm not really sure. And it says that you're going to remove every fraction. So we can't leave our answer as L over T. If I want to go to indices, remember that in indices, 1 over A is the same thing as saying A raised to power minus 1. So if we're going to do that here, we have that this is L over T, same thing as we're having L over T squared. That is L times 1 over T squared. That means we're going to have L times T raised to power minus 2, which means this our answer here isn't going to be L over T squared. Our answer is going to be L T raised to power minus 2. So we've gotten acceleration, L T raised to power minus, let's go put it down here. Let's open your bracket first of all. First of all, L T raised to power minus 2. Then we have T is also there. Then we have times T. Then plus. Okay, thankfully we've already gotten velocity. Velocity is L over T, which is the same thing as, L T raised to power minus 1. So let's go back and write it down here. L T raised to power minus 1. So now let's look at this. L T raised to power minus 2 times L is the same thing as saying L over T squared. Then I'm putting the fraction to be easier for you to understand, times T. T is in a fraction, is a whole number on its own. So let's just say T over 1. Let me just leave that T, not to confuse anyone. Which means that 1T will cancel this square, so that only one thing is remaining. Meaning the answer is now L over T, which is the same thing as L T raised to the power minus 1. So if we go back, let's now rewrite the whole thing. This L T raised to the power minus 2 is now L T raised to the power minus 1. So I told you about dimensionally correct. Dimensionally correct means that the first one has to be equal to the second one and has to be equal to the third one. So our first unit here is L. L is for S. Then AT, the formula for AT is LT minus 1. LT raised to power minus 1 isn't the same thing as L. And VT squared, then VT squared is not the same thing as L, which therefore means that this equation ST plus VT squared is not dimensionally correct. So let's just go back and let me just mark it wrong. Oh, sorry, not dimensionally correct. VT is not dimensionally correct. So the conclusion on this first equation is S equals A plus V, AT plus VT squared is not dimensionally correct. Okay, so I'm going to move on to the second one that says AT equals V plus U over 2. V plus U over 2. Okay. Yeah, that we have it that is equal to V plus U all over 2. 18 is equals to V plus U all over 2. So luckily for us, we already have a dimension for acceleration times time. We've got that acceleration is LT minus 2. For acceleration times time on its own is already LT minus 1. So let's just put it down quickly. LT minus 1. Well, first of all, let me just simplify this for you. They say, remember the 3 rules I said, first of all, write it down in its formula. This is the formula. Second of all, remove any constant. So we have a constant in this question. 2 is a constant because it's not part of a formula. So it's just going to disappear. Like there's no mathematical rule of saying this divided by this or this subtract this. It just disappears like that. So that means our equation is practically AT is equal to V plus U. So let's write our AT is LT raised to power minus 1 is equals. Now V means final velocity, U means initial velocity, but both of them are just velocity. Initial velocity is actually the velocity that a body used to start moving when it's about to start moving. Then final velocity is the velocity it has before it comes to a stop, or at a particular time you catch it or something like that. So we've already gotten a formula for velocity, which was LT minus 1. We got our velocity as LT minus 1. Yeah, that's it here. LT minus 1. So which means that just go back in there and write LT minus 1. This one is actually pretty faster and easier than the second one. And final velocity the same thing as normal velocity. So we have another LT raised to power minus 1. So LT minus 1 is equals to LT power minus 1 plus, and this is equals to another LT power minus 1, which therefore means that this equation is dimensionally correct. So we've gotten this one. AT equals V plus U over 2 is therefore dimensionally correct. So I want to solve the last question, which says that S is equals to UT plus AT squared. We have that S is equals UT plus AT squared. UT plus AT squared. So thankfully it's another set of figures that like what we used before. We know that L means distance. I'm just writing the L here. ut is going to be, and then write in a fraction for so that we can just do it quicker. LC minus 1, that is L over T for the velocity, times time, that is this T, plus the acceleration is length over time square, times another time, but this time is squared now, and then cover it. So let's do our math. We know that T, according to algebra, T cancels T square cancels another T square, which means our answer is going to be L is equal L plus L. So L is L and L is also L. All of them have the same dimensional formula, which therefore means that this third equation is dimensionally correct. Now, I know that most of you are familiar with this, especially this third one that says S is equal UT plus AT squared. So I'm going to say something about it. The original formula is actually S is equals UT plus half AT squared. It's the second equation of motion. So just to know that, I want to just help you guys know that just because there's something is dimensionally correct does not mean that the formula itself is correct. Okay? So you don't get yourself confused. This is the actual formula. But you know that if we're doing dimension analysis, this half will just go poof. It will just vanish because it's a constant, which leaving it as AT S equals UT plus AT squared. So that's just it. Just because something is dimensionally correct doesn't mean that it's the equation itself is a correct equation, so that we won't get ourselves mixed up. So I'm just thinking of a very fun idea right now. How about I give you guys an assignment for the road? Feel free to drop the answers at the comment section, and if you have any other questions you would like me to solve on, or like me to explain any topic you'd like me to explain, I will get to it, and I hopefully that you will share it out with your friends. So I'm looking for a very nice question here in my textbook. Which of these is dimensionally correct? So which of these equations are dimensionally correct? Okay, I'm going to have that T, question 1 will be T is equals X over A. The second one is T is equals the square root of 2x. Okay, so let me write it better. Let me give it more room. The second one will be T is equals the square root of 2x all over A. And let me squeeze in one more. The third one should be T is equals Vx, V over X. Okay, so I want you guys to know that X means distance. X is the same thing as distance. So you're just finding T. So number 1 is time is equal distance over acceleration. Number 2 is time is equals the square root of 2 times distance over acceleration, or time is equals velocity over distance. So I want you to find which one of them is dimensionally correct. Put your answer in the comment section. If you need an explanation for anything, feel free to contact me on my email that's there with your question. If I can do it, I will surely do it. If not, I will report it to my teacher's own channel, link it up to you guys to help you guys with it. Please share, subscribe, and any other common thing. Thank you. Love you. Bye.